So imagine that you have a rope which is 7 centimeters long. Okay, a rope which is 7 centimeters long, and you want to fold the rope. You have to fold it in such a way that it covers most area. It encloses most area. So the first question is, what would be that shape, that area maximizing shape? Now, if you put some restrictions, for example, if you want the enclosed figure to be a triangle, then in that case, what would be the area maximizing figure? What if you want the side lengths of the triangle to be integers? In that situation, how would you approach the problem? So we will talk about all of these things today. We will use a problem from the first level of mathematical Olympiads in India, PRMO. But the problem is just a pretext. You know what I do with problems, right? I use them to learn new things. So I want to share these ideas with you. My name is Ashwini Dashgupta. If you are new to our channel, consider subscribing it. We discuss beautiful mathematical problems and ideas in this channel. And for more information on our courses, check the link in the description. So these are called isoperimetric problems. Okay, the perimeter is fixed. So that's the main idea. Let me write it here. The perimeter of the figure is fixed. In this case, it is a 7 centimeter long rope. A 7 centimeter long rope, and you are folding it, bending it, making it a closed figure. So maybe it looks like this after you have folded it. If you are bound to make a triangle, so then you put restrictions on the problem, then it probably looks like this, a triangle with perimeter 7 and so on. So the question is this: what is the largest area you can enclose? So this is an area maximization problem. So here's a question. What is the largest area that you can enclose? Okay. So if you think about the largest area that you can enclose, you can actually think about it as a physics problem. That that particular space should be equal in every direction. Notice how I'm thinking about it. It should be symmetric. Why should it be symmetric? Because if it's not symmetric, suppose it's something like this, let's say, why something like this cannot be the area maximizing thing? Because then you can sort of stretch it. You can, let me draw that in red. You can stretch the same picture and put in more area. Your job is to make more area. So first of all, it has to be a convex figure. Convex means, what is convex? So I'll tell you a little bit about that. Convex means, this is not convex. This particular figure is not convex. What is the definition? The definition is that if you have 2 points in the figure, if you join them by a straight line, that straight line segment should be entirely inside this figure, which is not in this particular case. So this is not convex. So here the figure, the area maximizing figure must be convex, because otherwise, crudely speaking, you can simply reflect it, right? You can reflect about a midline and you can get more area to be included. So it should be convex. That's number one. It should look the same wherever you go. Whichever direction you look, it should look the same. Because if you stand here inside the figure, and if you look in this direction, and if you look in this direction, if they look different, if they appear different, then one space is doing better than the other. One shape is more efficient than the other in enclosing area. I'm just giving you a heuristic principle. It's not math. It's math, but it's kind of more like intuition, how the figure should look like. It should be convex. It should look the same wherever you see from a point inside. There is a technical term for this. I'm not going to use it. But what figure would that be? Can you put that in the comment section? Can you tell me in the comment section what figure would enclose the largest amount of area if you have no restriction? Now, the problem that came up in the Olympiad is a bit different. It asks, what if it's a triangle? Not only it's a triangle, it's an integer-sided triangle. So all the side lengths are integers. All the side lengths are integers. And they sum up to 7. So the perimeter is 7. What if the side lengths are integers? Then what is the largest area that you can enclose? So of course, we have to talk about area of triangles. Now, there are 4 different interesting areas of triangles, area formulas that I want to talk to you about today. There are more actually, but the first one is half base times height. It's very simple. You take a triangle, you drop a perpendicular, this is the height and this is the base. So half base times height is the area of this triangle. Why? So I ask this question all the time to our Math Olympiad students, the students in the class. I would say the area of the triangle in the class and I'd ask, why is that true? Now, most of you are reading this as a formula, so then you would not know why this is true. But can you think about it? Can you think why this formula of the triangle actually works? Okay, so this is the first formula. The second formula is sometimes known as the Heron's formula. So if the 3 sides of the triangle are A, B and C, you define the semi-perimeter S as A plus B plus C by 2. Then the area of the triangle is equal to S times S minus A, S minus B, S minus C. So you're describing the area of the triangle completely in terms of the side lengths, which is pretty cool. Again, the question is, why is the Heron's formula true? But you can try to prove that as well. If you are able to prove it, please put it in the comment section. Best commenter is still getting an award at Chidda, so please try to participate as much as you can. The third thing is the trig formula. The trig formula, which is very handy at times. So if you have a triangle, let's say A, B, C, and if this angle is theta, then the area is half AB times AC times sine theta. This is called the trig formula. Make sure this angle is the angle in between. Okay? And finally, you have the in-radius formula, it's basically if you have a triangle ABC, and if you have the angle bisectors meeting at the point I is the in-center, then this is, if you drop a perpendicular from here, this is the in-radius R, then you can find the area of the triangle delta. Delta is equal to half times R times A plus B plus C. A plus B plus C are the three side lengths of the triangle. So delta is equal to R times semi-perimeter. You can also think of it like that. There are other important area formulas for a triangle which are very, very useful in different contexts. Maybe in some other videos I'll talk about them. So we are interested in all those triangles, whose perimeter is equal to 7. The perimeter is equal to 7 and all the side lengths are integers, and we want to maximize the area of the triangle. Okay, so maximize the area of the triangle. All right, so now we come to the third important idea, which is the triangular inequality. So if you have ABC a triangle, then the triangular inequality says that sum of two sides it's greater than or equal to, actually it's strictly greater than the third side. Okay, sum of two sides is strictly greater than the third side if it's an actual triangle. There are like two statements actually which are very equivalent. The second statement is the difference of two sides. So two side lengths is less than the third side. These are equivalent, but one of them becomes useful in some occasion, the other of them becomes more useful in some other occasion. You add two sides, it will be larger than the third one. You take the subtraction, you take the difference of the two sides, it's smaller than the third one. Okay, so in this particular case, then you can check that if all the three sides are different, because the sum of the sides is 7, if all the three sides are different, then the only case that it can be is 1, 2 and 3, right? 1, 2 and 4. If the smallest side is 1, then the only way that's possible if it's 1, 2 and 4. If we want all the sides to be distinct. So that's 7. But there is a problem with this case. The problem is this: it does not satisfy the triangular inequality. That is, the sum of 1 and 2 is smaller than the third side, which is a problem, right? So this particular case doesn't happen. Now some people ask us, what is the proof of triangular inequality? It's really the definition of a straight path. That is, if you go directly from B to C, it's a straight segment, straight line. So its length will be smaller than if you go from B to some other point A and then to C. Okay? If you go from B to A to C, that will be larger. That's a larger path than if you go directly from B to C. That's simply the definition of a straight line. So the triangular inequality is in essence the definition of a straight line. Okay? Can you give me a similar statement for a quadrilateral? This is a challenge problem. Okay? For a quadrilateral ABCD, can you give me a similar statement? If you can, please put it in the comment section. We will call it the quadrilateral inequality. Okay? It's quite fun. Okay, so this one cannot happen. Then what is possible if the smallest side is 1? This is one way of counting the number of possibilities. you just try to fix the smallest side and then you gradually increase it. Okay, so the smallest side is 1, suppose. We know that it can't be 2 and 4. Then the only other case that is possible is 3 and 3. Yes, this is a case. This is possible. Then the smallest side, let's increase the smallest side's value to 2. So if it's 2, the remaining portion is 5. Right? Total is 7. 2 is gone. So 5 is remaining. So the second digit, it could be 5, could be done in many ways. We cannot do 1 and 4 because we cannot take numbers smaller than 2 because that case is done. 2 is the smallest number now. So the only case is 2 and 3 and 3 and 2. That's only possible. So 2 and 3, the same thing. 3 and 2 and 2 and 3 are same thing. So as the other case, can the smallest side be 3? Well, that's not possible because then 3 gone from 7, so 4 is remaining. You can't have a number larger than 3 to fit inside 4. Like it has to be like 3 and 1, but we know that case is already done, right? So we have only 2 possibilities. Only 2 possibilities. We use the triangular inequality in this case, right? Okay, so now the question becomes, which one of these 2 triangles have larger area? Which one of these 2 triangles have larger area? So we can use the Heron's formula, the one that is given here, this one. So the semi-perimeter in each case is 3.5. So 1 delta 1 is square root of 3.5, 3.5 minus 1, 3.5 minus 3, 3.5 minus 3. Okay, so that's square root of 3.5 times 1.5 times 0.5 times 0.5. Okay, so that's what it is. Now you can actually simplify this if you want. So this is 35 times 15 times 5 times 5 divided by 10 to the power 4. So if you take it outside the square root, this becomes 10 square. And the top one, you see that there are 4 5s here, right? In 15 is 3 times 5 and 35 is 7 times 5. So you have square root of 21 times 25. If you want, you could simplify this. So what is the other triangle's area? So delta 2. This is square root of 3.5 again. 3.5 minus, so this is 2 to 3. So this is minus 2, 3.5 minus 2, 3.5 minus 3. So square root of 3.5 times 1.5 times 1.5 times 0.5. So you can easily compare these two now. This one and this one. Here we have 2 0.5s. Here we have 2 1.5s. Clearly, this second one is bigger. Like the 2 is bigger. Right? So it's quite simple from here. Once you do the calculation, you don't even have to simplify. You can do it in a very straightforward manner, but just by comparing the stuff inside the square root. So I hope you learned something from this entire discussion. I would love for you to give me the results that I have asked for you, like the 2 questions that I have asked in between. If you want to do more beautiful problems and interact with the Chinta community, please consider subscribing. I will see you in the next video. Thank you and take care.